So a major disadvantage of the linear spline technique is that the function is not smooth. So at data points where we have two splines that meet, we call this a knot. And in the linear case, the slope changes abruptly at the knots or the interior knots. But we can apply higher order polynomials to solve this abrupt change. So in general, to ensure that the mth derivatives are continuous at these knots, a spline of at least m plus 1 order must be used. So if we wanted to use a third order polynomial, we'd have to ensure the first and second derivatives are continuous. And in most cases, a third order polynomial, in this instance, we would refer to a cubic spline. And although the third and higher derivatives are continuous, or possibly continuous, they often aren't detected visually and generally are ignored. Okay, but because the derivation of cubic splines is quite intricate, we'll deal with this in the next section. So what I want to do now is focus on illustrating the concept of spline interpolation with a quadratic spline. So our objective here is to derive a second order polynomial between the points, well, between a set of points. So let's say we have a function, or should I say we have data points. So we have 4 data points. This is x0, x1, x2, x3. This is interval 1 between x0 and x1, interval 2 between x1 and x2, and interval 3 between x3 and x2. And we wanted to fit some second order polynomials between these data points. Might end up with something that looks like this, where at each one of these intervals we have a quadratic equation, a1x squared plus b1x plus c. And I'm going to term the y values for my data points as f of x0, f of x1 at x1, and f of x2 at x2, and f of x3 at x3. Okay, so we have, for example, n plus 1 data points and n intervals. So here we have 4 data points, 3 intervals. And consequently, we'll have 3n unknown constants. So here we have 1, can write the other function, a2 squared plus b2x plus c2, and a3 x squared plus b3 plus c3. Okay, so we have 3 times n unknown constants. So let's count those out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 3 intervals. 3 times 3 is 9. So we have 9 unknowns. Okay, so therefore we need 3 times n equations or conditions. In this case, we would need 9. Okay, so the first condition, I'm going to switch to my black pen. We say that the function values at the adjacent, or the function values of adjacent polynomials must be equal at the interior knots. So in other words, I minus 1 multiplied by x squared at I minus 1 plus b at I minus 1 multiplied by x I minus 1 plus c I minus 1 is equal to the not value, f of x at I minus 1. But we also have the other condition that a of I, xi minus 1 squared plus b of I, xi minus 1 plus c of I must also equal to our interior knot. Okay, so this is now going from I equals 2 to n. And because we're only using the interior knots, each one of these conditions provides n minus 1, each polynomial provides n minus 1 conditions, so we have a total of 2n minus 2 conditions. Okay, second statement. The first and last function must pass through the endpoints. So we have two more additional equations. I'm not going to rewrite the polynomials, but if we have two more equations, then effectively we've gone from 2n minus 2, we've added two more sets of equations, so now we are at 2n conditions. Okay, we are still ill-conditioned because we have 3n unknowns. Okay, third point. The first derivative at the interior knot must be equal. So we know the first derivative of x is equal to 2ax plus b. And again, we are using the interior knots, and we have I equals 2 to n conditions. So this provides us with another n minus 1. So now we have 2 of n plus n minus 1. So we have 3n minus 1 conditions. Alright, so we need to now choose another condition that will help us alleviate and return to this value 3n. Well, we're going to choose an assumption that the second derivative is 0 at the first point. And this is because the second derivative of a quadratic function is generally 2a. And we could express this as being 0 by saying that a at the first point equals 0.